All right. How was your weekend? Are you ready for Thanksgiving? No, no. But it's the end of the semester. After Thanksgiving, 2 more weeks, and you guys are done. All right. Which is sad for me. Would you believe me if I told you that this group is one of the best groups I've taught?
Yes.
Would you believe me if I say that? Yeah. Okay, thank you. I don't know. I don't know. There's something special about you. I love the positive attitude, the commitment, the engagement. It's like you're just good group. So thank you. Ah, thank you. I didn't tell you that to get that, but yeah. All right. Okay, so let's go where we left off. Try to. I know it's been a long weekend, and you had a quiz on Friday, so your mind was occupied with the questions and how you answered probably. So let's just quickly try to remember what fat characterization is and why it's important. So give me examples. Yes, Emma?
It's important for perishability.
Perishability, yes. So rancidity is a big deal when you have fat in your sample. Even a small percentage of fat, like in flour, you have 2 to 3% fat in wheat flour, still cause problems. Or even in a protein ingredient that has 2 to 3% also, like pea flour, only 2% fat. But it really, really impacts flavor because of those oxidation products that are very potent. So that means that even at low concentration, they're going to have this bad of flavor. So, okay, rancidity. It could be oxidative. It could be, I know you struggle with the other one. Hydrolytic. Yes, very good. What else is important?
Functionality.
Functionality, yeah, like spreadability, mouthfeel. Also, it actually high fat food tastes good. So, yeah. What else? Processing effect. This is a big one because oils get processed to refine. They get hydrogenated. They can get what else? Deep frying in oil. So all these winterization, all these processes will impact the quality of oils or fat in food. Very good. One important thing that Ali always tells me, yes. So saturated fat, trans fat, cholesterol, these are all components that are important. Okay, very good. Now we can dive into the methods. And a lot of these methods we're going to be doing in the lab. So it's going to be a really cool lab, one of my favorite labs, although it's not proteins, but it ties up to all the tests ties up to each other, and we kind of solve some mysteries, which is really, really cool. Okay, so we're going to learn a little bit about physical characteristics of the bulk fat or oil, meaning bulk fat or oil, meaning like olive oil, corn oil, butter. So it's like the entire food is fat or oil. And then iodine value for degree of unsaturation, saponification value, it relates to the molecular weight of the major fatty acids. And then free fatty acids are important as indicator of age of oil, frying oil. Thank you, Vici. uh, Age of frying oil, degree of success of refinement, or hydrolytic acidity. So these are all important, and we're going to be doing some of those in the lab. Then we have the oxidation. Lipid oxidation is essential. So measuring present status, like right now, you have an oil and you want to determine the extent of oxidation. We're going to talk about primary oxidation, product measurement, secondary oxidation, product measurement, which you already covered in food chemistry. And then we're going to talk about evaluating of stability. So this morning in food chemistry, Fernando was talking about the kinetics of reaction, oxidations, accelerated shelf life. So we're going to talk about ways to measure that, ways to collect the data that Fernando was talking about this morning. And then we characterize the different fractions using GC methods, also HPLC methods, and thin layer chromatography. All right. Very good. So we're going to talk about all of that and hopefully finish today. We need to know some of that for the lab. Okay. So consideration, if we are analyzing bulk fats or oils like butter, ghee, lard, olive oil, canola, all of these different bulk oils and fats, we don't need to do any solvent extraction. But if we want to determine characteristics of fat or oil within a food, or an ingredient, we have to extract the oil first and then characterize it. So if you want to determine whether or not the oil or component of an ingredient or food is oxidized, first step is get that oil out. And then we use different organic solvents. Very commonly used is a mixed solvent to kind of be so that you're able to extract the polar and non-polar fats. So it's usually a combination of different solvents is used. Once you extract, obviously you remove the solvent, you get the oil or fat, and then you characterize that. No matter what you do, you really have to protect your sample from exposure to factors that might increase its either hydrolytic rancidity or oxidative rancidity, change the characteristic of the oil. So as you prepare, whether it is bulk oil or food sample that you're extracting the oil, really minimize heat, oxygen, and light exposure. So when you prepare a sample for analysis, and if you prepared that oil sample, let's say, extracted it, and you're not yet ready to do the analysis, you put it in amber bottles, so bottles that are not transparent to light, and you flush with nitrogen. So you flush the surface, you replace oxygen or air with nitrogen, seal really well, and put in refrigerated conditions or under refrigerated conditions. So you really, really want to protect that sample from any potential changes. Otherwise, you will have erroneous conclusions about your sample. All right. Physical characteristics. There are so many different physical characteristics that we use to kind of ID the oil or understand a little bit about the physical characteristics of the oil so that we can differentiate different oils and fats from each other and determine its impact or their impact in foods. Refractive index, it's usually if you want to ID the oil, certain oils have a specific refractive index. So you can look at references and kind of say, yeah, this oil is within the range of reported for refractive index. If it's not, there's something wrong about that oil. It could be contaminated, it could not be, or adulterated. Melting point is also important and characteristic. You know, oils exist as liquid at room temperature, fats exist as solid, but even different fats have different melting point. So it will be characteristic to the different oils and fat. Smoke, flash, and fire point. Do you remember what those are? So when you heat the oil, depending on the characteristic and degree of unsaturation or presence of free fatty acid, you will get, the more free fatty acids you have or the more degree of unsaturation you have a lower smoke point, so which is a temperature at which you see the oil starting to smoke. And then flash, you see a spark. Almost gonna be set on fire, but not yet. And then fire point. Have you ever seen oil on fire?
No.
You did? Where? Okay. I did too at home. Let me tell you a story. I have a story to tell you. Okay. So on my stove, I had a pot of water with eggs in it, and I had a pot of oil for deep frying my fries because I like deep fried food. So, and then I wanted to turn to boil eggs. What did I do? Turned on the wrong heating eye. And I left, went downstairs to work on my computer in my office, and then the alarm went off, the fire alarm. So I go up. Oh my gosh, the oil was on fire. My daughter was still young in her room. What should I have told my daughter to do? Huh?
Say no.
No.
Why?
What if the house got on fire? Get out.
Like if there's smoke, then she would have to go through the smoke and then she could stay in her
There's
room.
no smoke, there's fire. You should tell the kid, leave. I told her, stay in your room.
Okay, so
That
what
was,
did you
well, that was my first mistake. Then I took the pot. What did I do?
No. Did you pour water on water?
I opened the water on it.
Oh.
What happened?
What?
Boom! In my face, on the ceiling. It was a disaster. And it was still on fire. Okay, luckily it was winter, so there was snow outside. So I went to the deck, I opened the door, I threw the pot, and then what? Another explosion. The neighbor was outside. I ran in. I didn't want to sit the neighbors see me, but yeah, don't do that.
You rent it.
No, that's my home. I would have lost my home, but good, I have insurance. Yeah, so that's a story of smoke, past flash. It was fire point, definitely Legion. But one oil that you shouldn't really fry with is olive oil, especially if it is virgin olive oil. It will have a high degree of free fatty acids. It will have really low smoke point. Usually olive oil you use in salads, cold kind of food. You might use it to kind of fry an egg, but it's not necessarily used for cooking. The cold test and cloud point, they are related. They measure the degree, the properness of winterization. I remember what winterization is last time we talked about. To remove the wax. So you put the oil in at cold temperature, and then all this wax will crystallize, precipitate, and then kind of like clarifying your oil, especially when it's used in salad dressing. You don't want it to cloud. So to test the efficiency of winterization, you do a cold test and a cloud test. So the cold test is basically you cool it down to the same temperature that you would do during winterization and see if there's anything that precipitate. That means winterization was not complete. Cloud point, or you can just wait until it became cloudy. So same thing. Solid fat content and solid fat index. So you determine with these two things, you can do one or the other. You determine how much solid fat you have compared to liquid fat. It does impact smoothness, mouthfeel, how well it melts kind of in your mouth. The higher the solid fat content or solid fat index, the more solids you have compared to oil, and it does impact this consistency and spreadability as well. So we talked about adding olive oil to your butter, so it kind of help with this spreadability, and it reduces the solid fat content or solid fat index. All right, so more detail about that you can find in your chapter. You can read more of interest, but well-processed or winterized oil will pass cold test and cloud point. And then melting point, refractive index are characteristic of the type of the oil and the identity of the oil, and there are references that you could check. Finally, the smoke, flash, and fire point are impacted by the composition, fatty acid composition, but also processing. If you fry in the oil multiple times, you generate those free fatty acids, and then you will reduce the smoke, flash, and fire point. It's not good from a health perspective and from a processing perspective. All right, moving on. You will do iodine value in the lab. So when I ask you in an exam to define iodine value, the first 2 points you see on the slide are very important. So what is it? What does it do? Why do we use it? It measures the degree of unsaturation. So you really need to know what iodine value represents. It represents the degree of unsaturation. The higher the iodine value, the higher the degree of unsaturation. And then you really need to know the unit, because the unit will help you remember actually the equation you use to calculate iodine value. It's kind of a percent. So it's grams per 100 grams of sample. So grams of iodine picked up or absorbed by 100 grams of sample. All right. So it represents the grams of iodine per 100 grams of sample. So put a star next to those 2 points so that you remember them for this. The other thing you want to remember, not necessarily the chemical formula, but I want you to know that what do you use? What reagents you use? So you have a double bond, and then you use iodine chloride. So the iodine chloride will attack the double bond, and they will be absorbed by the molecule. So the iodine and the chloride will be taken up by the fatty acid within a triglyceride. But so in order for this reaction to happen, when you in your lab, so what you're going to do, you're going to put an excess amount of ICL. We're going to tell you how much to put, but in general, you want to put a lot of it in to make sure that there is enough to react with the number of unsaturated bonds. After the reaction is complete, you will have remaining ICL. So all of those excess that did not get absorbed by the unsaturated bond will remain. You will react the remaining, the excess, with, well, the remaining of the initial excess amount, you will react it with potassium iodide. Then you get iodine. This is the product that you will be needing to evaluate or assess the concentration of. So the iodine, the higher the iodine that is generated, the more unsaturated bonds you have. So that means, no. What's wrong in my sentence? Let's see if you paid attention or if you're following this concept. So if I have a lot of double bond, will I have a lot or a little of ICL? A little, yeah, less. The more double bonds I have, the less ICL remaining. The less ICL remaining, the less iodine I'm going to generate. Correct? Following, repeat, repeat. No, you're all good. All right. So, and then I want to use, by titration, I will determine how much iodine I have. Starch is added as an indicator. So starch and iodine will give you a blue color. And then I would titrate with sodium thiosulfate until colorless. So I titrate until all iodine are absorbed in the reaction, give me sodium iodide. And then the starch will lose its blue color. So I titrate to colorless. So you might be used to titrating until you see a pink color, for example. Yes. Yes.
More double bonds, less icy.
Left. Yeah. Left. Yes. So the more double bond, you will have more ICL reacting and then less remaining. The less remaining, you have less iodine generated. The less iodine generated, you would need less volume to titrate to reach endpoint. The endpoint is where all iodine is absorbed by the reaction and the starch no longer carries blue color because iodine is gone. So the blank, B is blank as a sample. So for titrating the blank, you need more volume or less volume? More, because blank will not have your fat in it, yeah? So all of what you had, all of the ICL will react with the potassium iodide and will give you the maximum iodine, the maximum amount. So the blank will have the highest volume of titration. That's why it's blank minus sample. I will all follow. Very important to remember that in this reaction, the blank takes up the most volume of the titrants of the sodium thiosulfate. Because all of the ICL will be remaining. There's no fat to react with. And then the largest amount of iodine is generated. And therefore, you need the highest volume of sodium thiosulfate. Your sample will be depending on how many double bond it has. So depending on how many double bond it had, so if it has minimal or it's very saturated, then this value will be really low because sample will be very close to a blank if you have no double bond. Does that make sense to you? Okay, very good. Now see this equation? It's really similar to that percent nitrogen that we derived, in the equation, right? So here, instead of, if you remember the Kaldal percent nitrogen, you had the molecular weight of nitrogen. This is the molecular weight of iodine. So 126.9 is the molecular weight of iodine. And so you have the blank is minus the sample is the volume. So in milliliters, the normality is for the sodium thiosulfide. And then you divide by the weight of the sample, whatever the amount of oil you put in your flask, which will be stated in your manual. And then you divide by 1,000 to convert milliliter to liter, right? Because normality or molarity is per liter, is moles per liter. And then you multiply by 100 because it's per 100 grams of sample. So it's a percentage, really. Okay. So review how we derive the nitrogen percent. It's the exact same. So you have here the molecular weight of the iodine, and then everything else is the same. Here, just remember that the blank will be titrated with a larger volume because you don't have the fat, you don't have double bond. All right, so questions. So it is used to characterize the fat. So in your book, you will have a table that gives you the iodine value, saponification value, and other characteristic for different oils. So you will be using that to see if what you do in the lab or the oils you characterize in the lab will fall in the range in that table. We'll talk about it in the lab. So it's a way of determining the ID of the sample. It is very important. You measure it after hydrogenation process. Because with hydrogenation, you're breaking double bonds, you're saturating the double bond. So after hydrogenation, if you are targeting complete hydrogenation, what would be your iodine value? Complete hydrogenation. What's that? 0. will be zero.
Oh, yeah.
Because you don't have anything, no double bond for ICl to react with. Okay, so always try to kind of remember the concept of the reaction, and then you will know that if it's a complete hydrogenation process, then the iodine value will be zero. So you usually, if you want to assess the hydrogenation process, you measure iodine value before and after. Okay. Another indirect measure of oxidation, because when those double bonds are oxidized, they are saturated. So if the iodine value is below the expected value, it could be oxidized. Okay. All right, are we good? Moving on. All right, saponification value is another test that you'll be doing in the lab. And again, put a star on these two bullet points when I ask you about saponification value and defining saponification value. It is an index used to determine the average molecular weight of triglycerides in a sample. And we will do an exercise to understand that one. It is defined as milligrams of KOH required to saponify 1 gram of sample. You have to remember the unit because it helps you remembering how this equation of equilibrium came to be. So in this case, it's how many milligrams of KOH needed to saponify 1 gram of sample. So saponification, you've done that for fatty acid analysis. So what does it mean? It's just you are de-esterifying and you're using a base. In this case, it's KOH. So you have your triglycerides, they will be saponified, meaning you are removing the glycerol and you are freeing the fatty acid in the form of potassium salt. So the OH will be picked up by the glycerol, whereas the potassium will be picked up by fatty acid chains. Then you will have potassium salt of fatty acid, and then to be specific, 3 of those, because 3 fatty acid in the equation, and then glycerol. That's why we need 3 KOH, because you have 3 fatty acids, 1 glycerol, you need 3 OHs to bring back glycerol and potassium salt. So that's the reaction. So here I would put excess KOH. So what you will be doing, you're going to use a flask, you're going to weigh in your fat, and you're going to put an excess amount of KOH. The KOH will be absorbed by the triglyceride, and then you will have remaining KOH. So whatever was not used, when all of the triglycerides are saponified, you will have a remaining KOH that can be titrated with acid. You use phenolphthalein as an indicator, and you will titrate until colorless in this case. So I think when you put the phenolphthalein, it will turn pink. And then when you titrate with HCl, the endpoint is colorless. Okay, so is that so? Or do we titrate to pink? Did you guys do it? I forgot if we titrate to pink or pink goes to colorless. I forgot. I forgot what's the phenolphthalein. You can look it up. Phenolphthalein color in base versus HCl versus acid. I forgot that. Anyway, so here also the blank will have the highest KOH remaining, because if you don't have fat, all the KOH will be present. So the blank will take the highest amount of acid. What did you get?
Oh, so
I was right at the first time. So titrate to colorless. Yeah, okay, good. All right, so the sample, some of the KOH will be taken up by the triglycerides, so the sample would need less acid to reach equilibrium. Okay, are we good here? So also the blank will be higher volume than the sample. Okay, so when we want to do the derivation, I have to think about my unit. So I'm milligram per 1 gram of sample. So if I go back, it's per gram of sample. Do I need 100 here? No, so it's not per 100 grams of sample, per 1 gram of sample. So no 100. If I need it in milligram, not gram, so do I divide by 1,000? No. So here, then we go here, there's no 1,000 in the denominator, and there's no multiplication by 100. So this 56.1 is what? Is the molecular weight of what? KOH. Yeah, the normality is the normality of the acid, the HCl, and the blank minus sample of HCl needed to titrate to reach equilibrium, and the 56.1 is the molecular weight of KOH. Right, and that's the saponification value. So if you remember milligram per gram, you know that I'm not multiplying by 100, I'm not dividing by 1,000. Okay. All right, now take out a piece of paper for a +2. And let's solve this. All right, so here's what I want you to do. And I want you to really think hard. I'm going to give you a few minutes, 5 minutes, to think hard about this one. So I want to determine the authenticity of my olive oil. Okay, so I determined the saponification value of this olive oil, and I'm asking you what would be the molecular weight of the main fatty acid in this oil, oleic acid, right? So I want to see if I reach the molecular weight of oleic acid, then it would be a potentially pure oil, not adulterated. So if the saponification value of olive oil that I'm testing is 190 milligrams of KOH needed to saponify 1 gram of fat, what would be the average molecular weight of the fatty acid in that oil? So that means, what's the average molecular weight of oleic acid in this oil? If the saponification value was less, okay, that will come to that. So now let's solve the first one. But in order for you to solve the first one, I put the chemical reaction here again. So it's triglyceride. In this case, I don't care for the molecular formula or structure. So just triglyceride reacting with 3 KOH because you have 3 fatty acids. So you need 3 OH to break, and heat, of course, to saponify and get the glycerol back, and potassium salt, 3 potassium salt of fatty acid. Another thing I want you to remember is when triglycerides are formed, when glycerol and 3 fatty acids are formed, it's a condensation reaction. So 3 moles of H2O are released. So if I want to think about molecular weight, I'm just going to say when I take 3 fatty acid and react them with glycerol to give me triglyceride, 3 moles of H2O are released. It's a condensation reaction. So you need this for determining 3 fatty acid. I gave you the molecular weight of glycerol. I gave you the molecular weight of water. So 3 times 8. So, but first, I need to determine the molecular weight of triglyceride using the given 190 milligrams of KOH per gram. So what you need to first find is the molecular weight of triglyceride. Now, how are you going to determine the molecular weight of triglyceride? I'm going to give you another hint to remember. So molecular weight unit is X grams per mole. So you want to find that. Molecular weight is grams per mole. In a chemical reaction, how many moles of triglyceride is reacting with how many moles of KOH? 1 to 3. All right. Now, armed with this information, find X. Why is Katie laughing? All right. All right, where do you start? Anybody where do you start? Using the 190 milligrams per gram and the fact that molecular weight is grams per mole and the fact that 1 mole reacts with 3 moles, I want one of you to tell me where to start. Okay. If nobody knows where to start, shall I proceed with how to start? Okay. Let's proceed with how to start. All right. So the first thing you want to do is make sure your units are unified. What's the saponification value? 90 milligrams of KOH per 1 gram of, let's say, triglyceride. Okay. So I want to convert milligrams to grams. How would I do that? Divide by 1,000. So dividing by 1,000, this will give me 0.190 grams of KOH for 1 gram. So now I have gram for 1 gram, right? All right, I'm looking for molecular weight. I'm also looking for a gram, okay, per 1 mole. So the equation is what? Tg, so 1 mole plus 3 KOH, 3 moles are reacting. So I'm looking for X grams in this 1 mole. How many grams I have in 3 moles of KOH? What's the molecular weight of KOH? 56.1, right? On the previous slide. So the molecular weight of KOH is 56.1 grams per mole, right? But I have 3 moles. So what do I do? Yes. So 3 moles have 3 times 56.1 grams in 3 moles, right? So all right, I'm solving for X. What other information I have? I said 1 gram will need 0.19 grams of KOH. So now I'm solving for X. So X grams react with 3 times 56.1. And then I know that 1 gram needs 0.19 grams of KOH. So I'll just do that cross multiplication. Does it make sense? Are you following? Did I lose you somewhere? Right? So I know that 1 grams of triglyceride requires 0.19 grams of KOH. I know that 1 mole reacted with 3 mole, and I'm trying to find how many grams of TG is in 1 mole, which is the molecular weight. I know the molecular weight of KOH, and I know it reacts with 3. So 3 times 56 grams in 3 moles. So I have 3 numbers, 1 unknown. So can you solve it? Can you tell me what X is? 3 numbers, 1 unknown. So 1 times 3 times 56.1 divided by 0.19, you get X. Did you get a number? Why? 1 times 3 times 56.1 divided by 0.19, you get the X. Any number? Yes. So 885 grams per mole. All right. So I just gave you the backstory for how I got to the 885.8. You might want to take a picture of the board for you to remember. And then now if I want to know what the molecular weight of fatty acid, that's where the equation comes back, that 3 fatty acids and 1 glycerol gives you 1 triglyceride and 3 water molecules. So then the triglyceride minus the molecular weight of glycerol plus the molecular weight of water times 3 divided by 3, because you have 3 fatty acids, you get the molecular weight of oleic acid. And that's the molecular weight of oleic acid. So your oil is fine, is good. So basically you apply this equation, 3 fatty acids plus glycerol equal triglyceride plus 3 water. You know, you got the triglycerides, you have the glycerol, then you can calculate the molecular weight of fatty acid. So basically, you determined the molecular weight of oleic acid, and you said, okay, fine. Now the question is, if the saponification value was less than 190, would the average molecular weight of fatty acid be less or more? It's an inverse reaction. It's an inverse, not reaction, equation. Look, it is, so you are dividing by 0.19. If you divide by a lower number, you will get a higher molecular weight. And also you want to think about the size of the molecule. The larger the molecule, the less grams you're going to have per 1 mole. The larger the molecule, the less grams you're going to have per 1 mole. Or, you know, the less amount, the less grams, meaning the less amount of KOH you need to supplementify with 1 mole. Okay. This is all recorded. You can go back here it again and make sure it clicks. All right. So the last, well, not, yeah, the last I can cover today is free fatty acids. Maybe I can quickly talk about peroxide